So thank you very much for that warm-hearted welcome. Let me tell you two things. One, when I graduated university, I did the standard North American thing at the time was to put on a backpack and get a Eurail pass and go around Europe. I did not come to Sweden. I did not get that far north. But I met many Swedes while I was doing that, and I was always impressed with the English of the Swedes. So I think probably you all speak English quite well. But the second thing I want to tell you then is even my Canadian born and bred students always say I talk too fast. So if I'm going too fast, put your hand up and do this, and I'll try to slow down. I have trouble slowing down. Anyway, so this is what the title of my talk is because I didn't know what else to call it. But I want to talk about this picture first. I don't know, there's kind of a bright sky, or lights you can't really see, but much has been made of me being only the third woman to win a physics Nobel Prize. And I think things are changing quite a bit. But this was my life back in 1985. This is actually 1986, just in case you can't see, because it's not really showing up very bright. But this is me, okay, as a young person. And we're actually in the city of San Francisco in California in the United States here, but somebody noticed that the store, it's a clothing store called Rochester Big and Tall. So all of the Rochester people that were there for a laser conference gathered here. So this, I will tell you, is my supervisor, Joao Maru, who he and I are getting the Nobel Prize together. All right? But this is the rest of the group, and you will see that I am the only one wearing a skirt. And I am indeed the only female out of that great big group. So this is what it was like 30 to 40 years ago, is that really we stood alone, the women. And I have to say, though, I kind of liked it. I kind of liked being special. So, my husband is here with me. You may not recognize him because he used to always have this silly beard. Okay. But on one Mother's Day after I gave him 2 children, he shaved his beard for me. So there we go. That's the 2 of us there. He's in the back. He's back there smiling because he doesn't like that. Okay, so the rest of my talk then is about CPA and how come I got to do it. So here, these are my photons. I was the only one in this group. I was one of 7 when I started. I took 7 years to get my PhD. I was very slow. And by the end of those 7 years, Gerard had 30 students working under him, so it was quite a large group. But I was the one given a project to do that had to do with high intensity. And what does that mean? The atom here looks like it's almost the same size as what this is the laser beam coming focused down on an atom. But you can only focus light. Like when you take a lens and you focus light, you think it looks like you're focusing to a point. But you can't focus light to a point. There is a limit, and the limit is the wavelength of the light, and the wavelength is the distance between the crests of the wave. And different colors have different wavelengths. So out of the colors that we can see with our eye, the longest wavelength we can see is red. All right? And so the distance is 600 nanometers, or 0.6 microns, or 6.6 thousandths of a millimeter. The shortest light that we can see is violet, and it's about 325 or 350. You young people can see shorter than what we can. In the same way, I don't know how many of you like to play your things on your cell phones. My son liked to do that. We also lose our high frequency in our ears, too. And so they like to see us old people and how deaf we are when we go up to high enough frequencies. It was funny, one day in the lab a few years ago, all of my students all of a sudden had to put all their hands over their ears. And I didn't know what was going on. I go, what are you all doing? And they go, can't you hear that squeal? I went, no, I'm too old. So it was bothering them, and I was deaf to it. So that was good. Anyway, so I will tell you that the smallest you can, my laser had a wavelength of 1 micron, or thousandths of a millimeter. And so that's this size here. An atom, I realize now I have to use the word angstrom because I'm in Sweden. Although it's not an SI unit anymore, but maybe in Sweden it still is. An atom is about 1 angstrom, or 1/10 of a nanometer, small. All right? So this is obviously not to scale. This is 10,000 times smaller than this. But if you want to do a nonlinear optical thing, what that means is that the atom will absorb more than 1 photon at the same time. To absorb more than one photon at the same time, both photons must be in the volume of the atom. And so that is really densely packed photons. And the density of the photons is what we call the intensity of the light. Okay? The difference is that intensity is area and with time, because time and length is equivalent when it comes to optics, because light always travels 300,000 kilometers per second. And to remember then, let me just see what my next slide is. No, okay. So how does one pack in a lot of photons? If you imagine that I had a laser, which I saw that somebody had one of these things here, so let's just see. Did I see that somewhere? Oh, it's right up here beside you. Let's see if the laser part is in there. Yes, there is. Okay, I'm going to shine it not in your eyes. Okay, so do we all see the red spot over there? And this room, I could actually do it. I could go to a window. Usually I'm closed in. And if I knew where the moon was, which I don't because I'm not an astronomy person at all, but if I did know where the moon was and I was shining it out towards the moon, and I actually stopped the light, opened it for a second, and stopped the light again, I would have a 1 second long laser pulse. The beginning of that laser pulse would be 2/3 of the way to the moon before the last of the pulse left my hands. It's amazing to think how fast light travels, but in 1 second, the first of the light would have gotten 2/3 of the way to the moon. I'll also tell you that this is about a 1 milliwatt laser beam. And the 1 milliwatt laser beam I can shine on my hand and it doesn't hurt at all, right? I'm sure you've all done this. We have these as cat toys, right? We can buy these things easily now. And it doesn't hurt at all. And in fact, this one is perfectly safe. I could put it in your eyes. I won't. But you should blink before it would hurt you. So 1 milliwatt doesn't hurt. And 1 milliwatt is a power because sort of like a running tap where the electricity you get charged because of power, it's just always on. But the energy then, let's put this, power is energy per unit time. So when we talk about laser pulses, the power is the energy in the pulse, or the total number of photons times the energy of each photon, divided by the length of time of the pulse. So for a 1 second pulse, a 1 milliwatt beam has 1 millijoule of energy. Okay? So now that looks like, well, that doesn't hurt me at all, that 1 millijoule of energy hitting my skin every second, so what? I will tell you that the paper that I wrote, the laser that I built that got me the Nobel Prize, only produced that amount of energy, 1 millijoule. That's all it takes if you have the surgery for LASIK surgery and you need to slice open the cornea. It only takes that 1 millijoule. We can actually machine the glass that's on the top of your cell phone with no more than that 1 millijoule. And yet I can shine it on my hand and it doesn't hurt at all. And the question is, why is that? That's because we're not using 1 second long pulses. We are taking all of the energy that's in that 300,000 kilometers that would be there for this one, and we squeeze it down in size to 1/3 of a millimeter. So it's because we've taken it down that sort of 12 orders of magnitude and squeezed all of those photons together. And then we use a lens and focus it down so that it's, just a few microns instead of the millimeter beam that I was shining. Now you have a lot of photons squeezed into a very tiny volume. And so you can imagine, we can all think about the density of water easier than we can think about the density of photons. And if you're standing in a shower and you have the steam all around you, you could take your hands and sort of throw that steam into your face and you wouldn't feel it because there's steam all around and it wouldn't be any different if any more steam hit you in the face. If you went to your sink and then got water though and threw that on your face because the water sort of spreads out, you would feel it, but it wouldn't hurt. Now you could go and take a fistful of water and freeze it in your freezer, then pull that out of your freezer and throw it at your face, but would you want to? No, you wouldn't, because it would hurt, because the density of water now is all in that ball and it's being thrown at you and it would hurt. So this is what we're making. The other way I describe it always is a laser hammer, right? If you push on a nail into a piece of wood with all your might, it's not going in that wood. But if you take a hammer and hit it quickly, it drives the hammer into the wood. So that's why I also say that I developed laser hammers. So this is how come it works if you put it to cut your anything clear now. I should also compare the laser that I built, which, well, I'll wait till I've actually shown you the laser that I built. But the reason I got to do this great project, and the reason I'm the one who gets the Nobel Prize out of Gerard Maru's other students, including my husband, is that I was the one that was supposed to take a lot of photons, and somehow I've lost some of these other levels, but it doesn't matter. These are the photons being absorbed going up, to make one photon with all the energy of these photons out in the XUV. That's what my thesis was supposed to be. Never worked. But nevertheless, in order to do that, I needed to have 9 photons, not just 2, 9 photons in the volume of an atom. And so I didn't just need a laser, I needed an intense laser. So these are pictures of 2 lasers that were there where I was working in Rochester. We had dye lasers, and dye lasers are short lasers. They actually not only have 1/3 of a millimeter, they're 10 times shorter than that, 100 femtoseconds. Or 10 to the minus 13 femtoseconds. They also had a laser at the laser lab for laser fusion. And laser fusion needs a lot of energy. And so you'll see it's a huge laser. Like, I should have had one, except that the laser's firing, so we were not allowed even to be watching the laser when it's firing. But a person would stand up this tall here. Okay, that would be the size of a person. All right, it's almost a football-sized field that this laser is sitting on. And it could produce a kilojoule of energy, or 1,000,000 times more energy than what my laser had, all right? So at the laser lab, we had big energy and we had short pulses, but we couldn't have them together. I will say that if you had put a short pulse into this, you would have a laser hammer inside the laser, and you would drill holes. In fact, when people first tried to amplify short pulses, they were a little surprised that when they looked at their laser rods, they would find out that it looked like there was an entire row of damage all the way up and down the laser rods. So they didn't know why at the time, but they knew to stop putting short pulses down their laser rods, okay? So for a while, we did not do it. So then Gerard Maru had this idea. So that's Gerard back in the day. I actually saw Gerard give a version of this talk, and he had my picture up in the corner. So I took his slide and put his picture up in the corner, because I've gotten used to it since October 2nd now to have my picture taken. Before that, I can tell you, my husband would tell you, all the way through our honeymoon, we have videos of me saying, would you put the camera down? I don't want to be photographed. So that's Gerard. And so here's this very simple, beautiful idea. This is what we want at the end. This is my laser hammer. So it's in a very short pulse in time and has a lot of energy. So this is the laser hammer, but if we had that in the laser amplifier here, of course that destroyed the laser amplifier. So now here's a very simple, beautiful idea that Gerard came up with. Very short pulse, make it a long pulse, right? Make it go back and put all the photons over a long line. Now you can amplify them up and be safe. And once you have all the energy you can out of your amplifier, then compress it back to being a short pulse, and you have the hammer here and not in the amplifier. Seems very simple, doesn't it? Like, why does one win a Nobel Prize for something so simple? But what can I tell you? It changed how high-intensity laser physics was done and understood. And so there I am, back in 1985. I'll tell you a few stories about this. One, because we have to be safety conscious, one must wear laser goggles. I will also tell you these laser goggles have green glass to make sure the infrared beam did not go in. But these don't look green, do they? And that's because they didn't like the picture of me with wearing green glasses. So they actually left the frames on so it would say I'm wearing safety goggles. But they actually took the safety part away. Am I being taped? I probably should be careful. So it was 30 years ago. This is the fiber that did the stretching. So when the short pulse goes into a fiber, the different colors travel different speeds. And so the reddest of the colors travel fastest, and the bluest colors travel slowest. And so that way, when they all started together, the red ran ahead of the blue and became a long pulse. Now, you might think that I calculated how long of a fiber I needed. You might have thought I did some kind of theoretical calculation. No. Gerard Maru phoned up Corning, and Corning Glass is in the town of Corning, which is just about an hour south of Rochester, and told them his beautiful idea and said, I need special fiber. This fiber is not the type that they normally did, because they normally do fiber for 1.5 micron light, which is optical communications wavelengths. We were working at 1 micron, and so they had the specialty fiber for us, and they very nicely donated 2.5 kilometers of this fiber. The problem I had was that they had it on a spool, and I could only get to one end, but I needed both ends to be mounted into my fiber mount so I could get the light in and get the light out. So I had to spend a day unspooling my 2.5 kilometers of fiber, and re-spooling it such that I could get to both ends. And then when I put the light down, it didn't come out the other end. So I had to look with my IR viewer to see where it was, and wouldn't you know, it was almost in the middle where I broke it. So I had the longer of the two pieces was 1.4 kilometers, and so I did, if you read my paper, you will see I used 1.4 kilometers without telling you why, but that was why. Luckily, 1.4 kilometers was long enough. Okay, 2 kilometers might have been better, but 1.4 was good enough. So this is me launching it, and here's the fiber. I will also tell you, you can see it's a very crowded lab. This is the lab that I showed you with the dye laser, all right? The pump for the dye laser was a neodymium YAG, which would match the neodymium glass that I was going to amplify it in. There was no room for me, so it was kind of advantageous that the first thing I needed was a fiber. Once we had it launched, we actually, a much smaller graduate student than me, who was also not afraid of heights and closed spaces, which I am, so I would not go through the air ducts. And technically, we should have asked a plant operations person, but we didn't. A small graduate student crawled through in the middle of the night when no one was watching and took the fiber down to the other end where we built the amplifier at the far end of the laboratory for laser energetics. So here is the picture from the paper, and this is, oh, I didn't know I still had that on there. I am bringing Marcel Bouvier as one of my 14 guests, because he was our electronics engineer who kept my laser firing for me. The electronics were a problem. So I'll just tell you this very simple layout here is that we started with the YAG laser I told you. This is the pump for the dye laser. But actually, the dye laser needed to be pumped in the green. And so it actually used this nonlinear optical idea of putting photons together in the atom. And they did 2 photons at a time to make twice the frequency, which is green. But that only takes about 10% of the energy. 90% of the energy was being thrown away. The leftover infrared was just being thrown into a beam dump so that it didn't hurt people, because it certainly would have caused severe burns. It could make paper go on fire if you wanted to. So that's the laser I used. And so it would look like that. And then out of the 1.4 kilometers, see, nowhere in the paper does it say that why. The idea is that you stretch the pulse in time. And by doing that, I will tell you that this shows you that the colors at the beginning of time, well, actually, this is the beginning of time, would be the reddest going to the bluest in colors. And then you go ahead and amplify it. Now, the beginning one in time, which is, this is wrong, it should be minus t, but it doesn't matter, gets amplified the most. Right? The beginning of the pulse goes through and sucks the energy out and leaving not so much for the trailing end. But that was okay, because we didn't amplify it very far. Now, of course, over the years, people have wanted to amplify it a million times more than this. And I was asked to write a chapter about trip pulse amplification just this summer. So I actually studied it myself this summer, because I knew the beginnings, but I didn't follow it all the way to where we are now. But I will tell you that now the people are making these up into the kilojoules towards the megajoules. They found this to be a problem because this was getting so steep and you want all of these colors. It was finding that they weren't keeping all the colors. So very clever people. They said, you know what? We can stretch it. Then we'll amplify it halfway. And then we'll not just compress it back to being short, but we'll compress it so much the other way and amplify it the rest of the way that now the blue colors are first and get amplified. And so the red colors get amplified more than the blue for the first half, and the blue colors get amplified more than the red for the second half, and they're back having all the colors they want. Very clever. But this is what I had. And then you take it off 2 gratings, and you get back a short pulse. And here's the one that showed, and it'll say thanks to Steve Williamson, the other person that I've brought with me for my 14 guests. Steve Williamson had the way to measure it. I spent a year building this laser. Morning, noon, and night, 7 days a week. I worked on this laser for a year. And then at the end, I had no way to measure. Do I have a short amplified pulse? How will I know? Luckily, my colleague Steve Williamson had a device called a street camera, and it could measure it for me. So he came in one night with me, and we worked away. This is just the calibration to say that through something called an etalon, it would have a reflection, and we knew that the reflected light would be exactly 125 picoseconds. So then we could count how many pixels was that, and we knew how many pixels was the pulse duration. And it was the picosecond that we hoped it to be. So just a few humorous stories. Yeah, I've given one up. So that's all right. I'll just tell you about these 2. So it went out in the newspaper. It actually got out in the New York Times that we had built this. And 2 students then at the university wrote an article to the University of Rochester's newspaper, upset with us. You have to understand this was in the Reagan era, and he had something called Reagan Star Wars going on, and this is why people working in lasers had a lot of money to work on lasers, okay, because they were hoping we would blow up Russian missiles. And so you'll see this is what we got accused of, because we said we wanted to do atomic physics with it, and they said they don't want to do atomic physics with it. They want to blow up Russian missiles. And I'm thinking, I'm just a little Canadian. I don't want to blow up anybody's missiles. All right, so now one student was a political science student, so I could forgive him. The other one was a mechanical engineering student, and I kind of thought he should know the difference. But anyway, we invited them over, and we put down a little toy missile to show we couldn't even knock it over, let alone blow it up. So again, we have enough intensity that we could shove 7 or 9 photons into one atom. But what we don't have is a lot of energy. We had a lot of photon density, but remember the energy that we had is still the same energy that I was able to shine on my hand and not hurt it. So yes, if you focus it right down to micron sizes, we could put micron-sized pits, holes. So if a missile would just stand still long enough for us to micron by micron by micron destroy it, we could destroy it, but not very many missiles were going to just hang around. And our laser only fired once every 30 minutes. No, every 30 seconds. So this one was every 30 seconds. The really big ones were every 30 minutes. Mine wasn't. Mine was every 30 seconds. All right, so even so the missile has to really stand still for a long time. So that was not, And the other thing I should tell you is the laser didn't work the day they came over, so we couldn't even show them that, and that's really why you wouldn't want it to be ready to blow up your missile. It was a pretty finicky laser. All right, so this is the other one I loved, is that we got a letter in the mail from somebody in the state prison, just an hour's drive away from Rochester, saying how can he get one of these CPA kits. He had bought a laser kit, and he had built himself a laser in the jail cell. Now he just wanted a CPA kit, and I kept thinking, okay, he's just trying to dig himself out of that jail. He just thinks that we can just, and again, he would have been sorry to see the fact that it would be micron pit by micron pit, and it would be easier just to take a shovel and get going. So anyway, those are just some of the humorous stories, and I'm going to finish here. There are no pictures of Gerard and I together from back in 1985 by ourselves, so we were at a conference just a few years back in Calgary, Alberta, and we took this picture. So thank you very much.
Hello. Hello. I'm Tintin. I'm a 3rd year.
Pleasure to meet you. My name is Sarah, and I'm also a 3rd year.
My name is Tuva, and I'm a 1st year student.
My name is Felix, and I'm a 2nd year student.
Okay. Is there a 4th year, or is that just 3 years?
It's 3 years.
Okay.
Yeah. So you said during your presentation that you went on a trip after university, but that you didn't visit Sweden.
No.
But have you visited since, or is this the first time you're in Sweden?
This is my very first time in Sweden. I was jealous that my husband, who was not my husband at the time, when we were still in grad school, he got to come here to represent Gerard and give a talk at a conference, and he came back and he brought me a lovely piece of Orpheus crystal. So I have that on my mantle, but I have not gotten to come to Sweden before.
Have you ever wanted to visit any place in particular in Sweden?
Oh, any place in particular other than Stockholm? Well, of course, Lund University is where, one of the reasons that I ended up not doing where I showed 9 photons coming up and 1 coming down. While I got the CPA, a woman named Anne Louvier in France did the 23rd harmonic. So it was like, why bother trying to get the 9th harmonic when somebody's blown me out of the water and gotten the 23rd harmonic? And she's now at Lund. So I'm going to Lund after this. So I've always wanted to see her lab in Lund. But yeah, you're asking me more about general things. No, I actually just wanted to come and see Stockholm and see how pretty it was. I saw all of Doug's pictures of how pretty everything was.
Too bad it's pretty cloudy.
I know, like hopefully I can come in the
weather.
summer when I have long days instead of short days too, yes.
Right. So you're obviously very proud of your prize, I suppose.
I suppose so, yes.
But, personally speaking, what does this prize mean to you?
Well, it's one of those, it's funny, it's both a humbling and a proud thing all at the same time, right? I mean, people keep comparing me to Marie Curie, which is just ridiculous, okay? Like, there is no comparison between me and Marie Curie. And so I find that a little bit hard to take. But on the other hand, the the other thing that's very strange about this prize is that I did do this work 30-some years ago. And I have certainly been recognized for it over the years in the high-intensity laser community, right? I've had many invited talks, and I was voted in as president of the Optical Society, and so I've been well known inside the laser community. What the prize does is it makes other people know about you. And so it's a very strange thing, because I even walk around my own university and now people want to meet me. And it's like, really? Because I did this work 30 years ago, and I've been walking here, and you could have seen me at any time and talked to me about it, but you didn't care, a few months ago, but now you do. So it is kind of a strange thing. It's not like I did something and then got recognized for it, right? So that's what's a little strange about the whole process here.
Did you ever consider receiving the Nobel Prize in physics?
I would have people ask me about it. I don't think that I thought about it. And I certainly, again, I knew that it would be, when we built it, we knew that it was a new way to get high-intensity lasers that had not been able to be reached before. And so we knew that it was going to be very big in the world of high-intensity laser physics. But that doesn't mean that that makes it a big thing in order to win a Nobel Prize. And I was surprised that it only took 10 years until they figured out how to cut the eyeball, the cornea of the eyeball. So I knew it would be big, but I'm a little surprised it's this big. But certainly the other people in high-intensity laser physics, when they would meet me, they would say, "Don't you think you're going to win the Nobel Prize for that?" And I go, "No, I don't think so."
What was your reactions and your family's reactions to you receiving this prize?
Well, my favorite one is my daughter. I'll have to say my husband is enjoying being one of the very few male spouses ever. But my daughter, who is in her first year of PhD program in astrophysics, she unfortunately this summer had her email hacked, okay, which upset her very much. But then I only texted 4 people after, like, I hear about it at 5 in the morning, and I texted my brother and my sister and my son and my daughter. And I knew that my son and daughter would not be up at 5:15 in the morning when I texted them. But when she woke up, she sees this text. And she said, "Oh, poor mother, her phone's been hacked." And then her girlfriend texts her and says, "Wow, I can't believe your mom won the Nobel Prize." And she actually texted her friend back, "No, her phone's been hacked." So that's how much my daughter thought I would win a Nobel Prize. And her friend had to say, "No, it's on the news." And so then my daughter Googled me, and then she phoned me, and she was like crying and screaming, going, "Mom, you've won the Nobel Prize. I can't believe it." I go, and she actually put that on her Facebook page. And then she was surprised because her PhD supervisor is very much about women in STEM. And also, I think as Canadians, we're such a small population that we don't win Nobel Prizes every day either, right? And so he had already, he obviously gets up earlier than my daughter, had already put out a Canadian woman has won the Nobel Prize. And then he reads his own student's Facebook page, I guess, saying, "My mom won the Nobel Prize." And he goes, "Okay, it's even closer to us. Our own Hannah Dykhar's mother is the one who won the Nobel Prize." So she was very excited. My son is studying comedy, and so his class was not as much into it, although he was ribbed a lot for being now the son of a feminist icon. So, because in the comedy world, that was something to be ribbed about. But no, I think, I've been amazed at the reaction of most people. At the press conference at the university, they had me on the first day. And again, I've been up since 5, and it's a very surreal thing to be given the Nobel Prize. I mean, very few people get to win a Nobel Prize. And so you're sitting there trying to absorb the fact that you are one of those very few people. And next thing you know, I'm in a press conference, and I realized I didn't get dressed up for it. And I sort of, my mother's passed away, but I still I sent out an apology to her anyway, because I knew she would be quite upset to know that I had not gotten dressed up for a press conference. And with all the cameras there, and I'm just sitting there like a deer caught in the headlights. And the former chair of my department, who I was associate chair under, he stood up to say how proud the whole department was of me. And that's when I looked to see each person. And each of my colleagues was there with this beaming face. And I went, "Oh my God, I can't believe it." I was almost in tears. So I said, don't keep talking, Rob, or I'll be crying in front of the cameras.
But what are your future plans after this?
What are my future plans? Well, I think my students hope that I find some more time to be with them in the lab. because I will travel a lot, this is like I now have the job of being the Nobel laureate. It is an almost job in itself in that I'm already being invited out to give talks to 2020 at this point. And so my schedule is very full doing that. So they will let me out of a year of teaching. But it just turns out that in January, I am to teach the lasers course. And I went, I think this is the year people might want to take a lasers course from me. So I'm going to team teach it. And so there will be another professor really in charge of all the marking and stuff. But when I'm in town, I will be the one teaching the lasers course so that people can be taught by the Nobel Prize winner that did it for lasers.
You worked on CPA while taking your PhD, and why did you choose to work specifically on lasers while doing so?
Well, I went to the University of Rochester because it was one of only 2 schools in North America to do optics, so I did know already that I wanted to study lasers. I don't know that I wanted to study short pulse lasers. That hadn't really occurred to me, although I have to say that after my second year, I worked with a person who was already working on short pulse detectors for fast measurements. And so I guess I'd already been introduced to the idea even as an undergrad. But then just my very first week in Rochester, they have something, there was a colloquium on Wednesdays, but the half hour before the colloquium is called donuts, and North Americans love their donuts. And so they said, everybody come. So I showed up that first Wednesday. I wear something called an iron ring, which means that I did graduate from a Canadian engineering school, which also when I traveled around Europe, we all found each other and we went, hey, you're a Canadian. And so this other Canadian was there and he saw the iron ring and he came running over to me. And he goes, oh, I heard another Canadian was coming here. And he asked what I wanted to do. And I said, lasers. He went, oh, I have the person that you should meet. And he, the very next day, took me to the laser lab. And I went into that lab that had the red and green laser beams and thought, that's so much fun. And he introduced me to Gerard. And I asked if I could work with Gerard. And that's how I got to do it.
You explained the process very well. I suppose it was not that easy working on the thing, and considering the fact many of us have trouble finding, to solve simple equations. How did you know that you were doing, the right thing, that you were on the right path?
Oh well, a lot of times you don't, right? A lot of times you stumble. And so this is actually the fun part of science, though, right? I like to solve puzzles. And so the one puzzle I can tell you that we got is that when I showed you the spectrum where it's big at the front end and back, and there was some small ripples, but when we first measured it, there were huge ripples in it, and that would mean we were going to get multiple pulses, and we went, what the heck is that? That's not supposed to be there. This idea is that we should just amplify it and everything stays the same. And so that was one of the things that we had to realize and we had to puzzle. And I have to say that both, Gerard and I would talk about that, but the group would actually have weekly meetings, and every time we have a problem, we would discuss what we think the problem is. And eventually, we realized that inside the type of laser amplifier I had, we had a piece of glass that usually, if you're not trying to amplify a lot of colors, and you need a lot of colors if you're going to have a short pulse, it doesn't show up, and you can have that piece of glass to do what it was supposed to do. But that piece of glass is an etalon. So if you saw that I used something that I said was an etalon to say 125 picoseconds away, that's actually a thick piece of glass. Our thin piece of glass was making it rattle around so that the pulses would be coming out in time, and in a spectrum, then that gives you this modulation. So we had to work, so we knew the glass was the problem, and then once we knew we had to take that piece of glass out, we still needed what it was to do in the laser, we still needed to do. And so that was the next puzzle, is how to do it without that piece of glass. So nothing is quite like you think it's going to be, because otherwise there's no point in doing science, in a way. If it's so obvious, then why even bother studying it? So it should be a challenge, and I think the challenge is what's fun for scientists. And each step of the way, we just had to keep figuring things out.
Lasers is usually shown in fiction. Is there any fictional lasers you wish were real?
No, the fictional laser that, so I actually have a demonstration laser that I take out when, the undergrads actually do a lab with it, but I also demonstrate it to smaller students, and not younger, I should say younger students, sorry. So I was doing, I think it's grade 8 students at home. One summer I was working because my daughter's friend was the counselor, and she asked me if I would do a laser demo every Thursday for her. Each week was a different group of kids. And of course, the one that they always ask about is the silly lightsaber. So I pointed out, so I was just actually at a Girls for Physics thing last Saturday, which is less than a week ago, I guess, just before I came here. And that's what I pointed out, is that the glowing amplifier is what a Star Wars, is it Star Wars or Star Trek? I don't know. But whoever needs a lightsaber, I said, it's just a light bulb. It's the stupidest thing. Why do you care about a silly, just long, fluorescent light bulb? I mean, come on. Because the point about a laser is that the reason it is so much stronger and it can do these nonlinear things that regular light cannot is that it is in a beam, all right? And it's in a beam, and I'm not going to shine it in your eyes, so be careful, or I'll be careful. You'll see that you can see the light when it's scattered off the wall, but you do not see the light going. And the reason you do not see the light going is for you to see something, the photons must go into your eye and register at the back of your eye in the retina. So if the laser beam goes this way, it can't be going into your eye, and that's why you don't see it. And so a laser beam is much better than a light bulb. But somehow having that glowing stick was supposed to make you think, woo, that's a really scary thing, when really it's just a light bulb and the light's going in all directions, and so it's useless. Anyway, so that's my beef against lasers inside movies.
When did you know that you wanted to study physics, and why did you choose optics?
I think I like optics because you actually see it. So that's the one. That's why I like about lasers, I think. How did I know about physics? I'll tell you a couple of stories. I do know that I enjoyed my physics classes and stuff. I actually won the prize for being the top student in grade 11 physics. Now, my grade 11 physics teacher, actually partway through the term, the computers were broken. I don't know if computers break as much now, but those days, computers were still new and they broke. And so he was having to handwrite in the report card for me. And so I stood there and watched, and whatever mark he gave me, he said, is this the beginning of a physics career? Now, with the Big Bang Theory, at Waterloo, physics is now cool because the guy who invented the BlackBerry started this Perimeter Institute for Theoretical Physics, and so physics has become cool. But in my day, physics was very nerdy. And I remember being really almost embarrassed to go across the stage to get the prize for being the best physicist, because I thought, oh my God, just hang a sign, nerd here, over me, like what's going to happen, right? And he wrote on the report card, is this the beginning of a physics career? And I said, I hope not. But then when I walked across, so that was halfway through the term, and at the end when I walked across the stage to get this prize, thinking, how am I going to live this down? It was a great life lesson for me, because so many kids walked up to me and said, wow, it must be so great to be that smart. And I thought, oh, okay, people aren't putting me down for it. They actually are thinking it's an impressive thing. So I guess I won't be embarrassed by it. But I was an unbelievably shy kid, unbelievably shy. I was the kind of kid that was always the cool floor where all the sports stars of the school sat and stuff. And the one year they even put my locker in that. And I went, are you kidding me? Are you making me walk down this hall? Every other year I walked all the way around the thing like this so I wouldn't have to go down that hall. That's how shy a kid I was. Stupid way, if you're shy like that, it's a stupid way to live. I actually went to a university where I thought I won't know anybody, just to force myself out of it.
You said you were really interested in optics because you can see it, but is there any other field in physics that you're interested in?
Well, I love physics, and I'm somebody who likes to go to the colloquium and hear about all these things. I mean, I understand why my daughter is into astrophysics, because it is cool to look at the stars and just ponder how unbelievable our universe is, right? So I can see studying that, but I've said to a few people, my favorite toy was Lego, and so I like to actually build things. I also thought I might have done what we call solid-state physics. Now we seem to call it condensed matter. I don't know why the names have to change, but anyway. I still kind of like lasers more than that, but and also in that same summer job where I worked on these short pulse detectors, I had to what's called silver paint this little teeny wire from there to here, and my hands shake a lot. Like holding them, you don't think you're shaking, but if you look at them under a microscope, my hands shake a lot. Well, the technician that I worked with was so mad that I could not silver paint this silly wire onto this thing, and I said, I can't do it. It just won't stand still, right? So he thought the answer was for him to put his eye through one of the microscope things while I put my eye through the other. All right, you think this is going to make my hand more still? I don't think so. And then he's going, what is wrong with you? You're young. Why is it your hand's shaking so much? I went, I don't know, but it does. So that kind of convinced me that, the small solid state stuff I probably shouldn't do. So, so the universe is big and the nano is small, but the lasers are just Lego size, and I liked it.
Can you think of anything one should know to become a successful physicist?
You should do it if you love it, because if you don't love it, you won't work hard enough at it. But if you love it and you want to do it, you'll have the perseverance to do it. I think if you're going to be an experimentalist, I will tell you it requires a tremendous amount of patience because, and certainly for lasers, we build them all day and then overnight, if they don't work through the night, the temperature changes a bit and everything, and you have to start again. And so a lot of times we will come in at 8:30 in the morning and we will tweak our lasers to 4:30 before they finally work, and then you start the experiment. Okay, and then, you know, whenever you shut it down, you know that you're going to have to start that all over again. So, and that's probably true in many fields, and so you'd have to know you have that patience. But again, I don't have very much patience for a lot of things, but I will keep retweaking lasers over and over again. So as long as you love doing it, it doesn't seem so bad.
I guess you're now a role model to many, I guess, young people and young women. Did you have someone that you look up to?
I've been asked that question a lot, and I don't remember. I think the word role model came long after me. I don't know when that happened. I think it's my mother probably is the one who affected me the most. She was a stay-at-home mother for much of my growing up because my dad insisted on that. But she did have a university degree, and she came from a small town where very few people went to university at all, and even fewer women. She also was good at math and science and got told in the 1940s that she should not go to university for math and sciences because she's a woman. And so she did go for English and history. And she was an English and history high school teacher. But she's all the way growing up, I heard, that was so stupid of me. I would have been so much better in math and science. Why did I let anybody tell me that I should do English and history? I should have always done math and science. So I grew up with this strong-willed woman who realized that she didn't follow her own dreams and that she certainly didn't want that for her children. And so I would say that she's probably the one who made me the way I am. And actually, I will end the story. My dad was told he was going to die when I was just about 10. I did not know it at the time. And he was given a year to live. And so she did go back, and luckily for her, she could get back into, and it was my high school that she taught at, which is a little bit strange, to have your mother there too. In fact, my grade 13 physics teacher, every time I didn't do well on a test, would go and say, Donna couldn't have studied for that test. And I was, come on, he's not telling every other parent. Why do I have to be told every time I don't study hard? But that's why she decided she needed a job, and my dad could not complain anymore about her working. And then he lived another 20 years. He did not die, so that was all good news. And we bought a cottage, and I said, aren't you glad Mom worked? Like, if you just had let her work all along, do you know how much more money we would have had? And it would have been great. So he came around eventually, too, seeing that women should be allowed to work. So.
Are there any particular works that have received a Nobel Prize that fascinates or inspired you?
Oh, well, I love, of course, the laser ones to start with. I mean, and actually, they're really only the only ones I really know about, and the laser cooling one. And I was very happy to hear that Art Ashkin won for laser tweezers. Certainly, a lot of us thought that he should have won years ago because the laser cooling used his laser trapping in order to do laser cooling. And so we were all well aware that why is one thing more fundamental or more beautiful or more what have you. So I was thrilled to hear that I was sharing it with Art Ashkin. So I have to say that I know the laser ones more. I did get to see Brian Schmidt when I was in Australia, and my daughter was with me in Australia for his public lecture, and he's the one about the expanding universe, and he gave a fabulous talk about that. But so, and my daughter and I took my, and actually, you know, I asked my daughter who was in high school at the time. I said, you can go out sightseeing, or this astrophysicist is giving his Nobel public lecture. What do you want to do? And my daughter said, oh, I want to see an astrophysicist give a lecture. So, which is good because she's gone on to grad school in astrophysics, so she knew early on what she wanted to do too.
The first ever laser was built in 1960, and you were born in 1959. Mm-hmm. Do you think there are any connection that you and the lasers are basically the same age?
I always say that I was born with the laser. There is that year difference, but I mean, they were trying in 59, so maybe we could say we were conceived at the same time. So yes, I always talk about how I'm the same age as the laser, and that maybe that's what it is. I'll also tell you that my mother will tell you the reason I love lasers is that when I was about 10, there was a brand new science center still there in Toronto, and my dad, who was an electrical engineer, showed us the laser and said, you know, this is the way of the future. You want to see this, and so she thinks that's why I was fascinated by lasers ever since, because I was a daddy's girl. I talk about my mother being the strong woman and the inspiration, but I was always a daddy's girl. So if he told me it was something good to do, I would think it was something good to do.
Thank you so much.
Thank you.